Oh, now I'm recording. Okay, so we're going to talk about the evolution of the energy density. How does it change with time? Here's a cute figure from the book I used for Astronomy 260, which is cosmology for people that took Astronomy 111, did well, and want to learn more but aren't astrophysics majors. That's the title of the course. Well, not really, but it really should be the title of the course. It's a really entertaining book, as a matter of fact. I think it's called Your Cosmic Connection or something like that. I should find it. But anyway, it's hilarious. I mean, they just, the authors are very, very funny, as a matter of fact. But in any case, so in order to explain how the density of matter changes with the scale factor, they say, imagine filling a box with mosquitoes. Ew, but anyway. So as the universe expands, our 1 meter cube becomes later a 2 meter cube. These are intergalactic mosquitoes, so they're in part of the universe that is expanding. And so matter is just sticking around as the universe expands, right? We're not creating more mosquitoes or anything like that. And so clearly, you got the same amount of matter, and now it's in, if the scale factor changes to be 8, by the time the scale factors become 8 equals 2, then our 1 meter cube has expanded into a 2 by 2 by 2 meter cube. The volume is 2 cubed as big. So the density is only 1/8 as big. In other words, the energy density associated with matter, the equivalent energy density, the mc squared energy density associated with matter, scales like 1 over the scale factor to the 3rd power, simply because that's the factor by which volumes increase. On the other hand, if you consider dark energy, if dark energy is indeed just this intrinsic energy associated with empty space, and every cubic meter contains the same amount of it, then that density stays constant, because as you create more space, you create a proportionate amount of dark energy. So that would be like mosquitoes that keep doing the mosquito thing of making more mosquitoes. And these are mosquitoes that somehow, don't need anything to reproduce themselves. We don't need to worry about conservation of mass or anything like that. And so these disgusting dark energy mosquitoes, by the time the scale factor was 2, there would be 8 times as many of them in that original volume that now expanded to be 8 times as big. And so the energy density would stay constant for the dark energy, if indeed it is a cosmological constant, just an energy associated with every cubic meter of empty space. So, if you had a universe that was made only of matter and dark energy, and dark matter would behave the same way as baryonic matter, so it applies, same argument applies. If you only had matter and dark energy in your universe, then run the clock backwards, allow the universe to shrink back towards the Big Bang. The dark energy staying constant, but the dark energy density staying constant, but the matter density is getting bigger and bigger and bigger and bigger as everything gets closer and closer together. So even if, as we think today, dark energy dominates the universe, there would be a time in the past when matter dominated the universe, because as you run the clock backwards towards the Big Bang, the matter density grows without limit, whereas the dark energy just stays constant. Its dark energy just stays constant. So in other words, what dominates the universe changes with time, is what it comes down to. And then meanwhile, though, there's another contribution, namely radiation to the energy density. And so with radiation, think of it as photons. As the universe expands, and it turns out it's most of the radiation energy density is in the cosmic microwave background. Stars have been emitting light for billions of years. but it turns out the total energy content of the cosmic microwave background is way bigger than the total energy content of starlight in the universe. So as the universe expands, the cosmic microwave background photons act like the mosquitoes in that pretty much the number of them stays constant. Yes, stars are adding more photons, but it's almost all cosmic microwave background photons that count, and those pretty much don't go anywhere. In other words, they're not absorbed by very much, and so pretty much the total number of CMB photons is staying constant, but they're getting more spread out as the universe expands. So that by itself gives a factor of 1/8³ for the radiation density. But what else happens to photons as the universe expands? They get redshifted, right? They get redshifted. So when the scale factor doubles, all the CMB photons now have twice the wavelength they had before. What does that do to their energy? By how much? Yeah, right? So when their wavelength doubles, E is hc over lambda for a photon. It goes like 1 over lambda. So when the wavelength doubles, each photon only has half as much energy. So in other words, that's another factor of 1 over the scale factor, because the energy density goes like 1/8⁴ for photons, because you've got 1/8³ from their being spread further apart as the volume of the universe increases, if you will, or each co-moving volume increases. And another factor of 1/8 due to the energy per photon diminishing due to the redshift. So matter goes like 1/8, the matter energy density goes like 1/8³, the radiation density goes like 1/8⁴ power, and the dark energy stays constant. And so here is the universe today. I'm sorry, it's not today. Here's the universe today is time since the beginning of the year, so 10 billion years. We're at about, this would be 10 to the 11th years. We're at about 15 billion. The universe is about 14 billion years old right now. So we're like right about here, okay? So today, dark energy dominates. It's the primary contribution to the energy density, followed by matter, followed by radiation. But if you run the clock backwards, so that you go back towards the Big Bang, the dark energy density stays constant. The radiation and matter energy densities increase as you shrink the universe. But since radiation goes like 1/8⁴ power, and matter goes like 1/8⁵ power, radiation increases faster as you go back. The radiation density increases faster as you go back toward the Big Bang, or turning around, it decreases faster as you go away from the Big Bang. And so the idea is that here's a plot of the radiation energy density with time. Here's a plot of the matter density with time. Dark energy density stays constant. So when the universe was, I think it was like about 9 billion years old, is our estimate of when the matter density and the dark energy density became equal to one another. And then following that, dark energy was the primary contribution. And so the universe is now dark energy dominated. We live like in the dark energy era now. We used to think we lived in a matter-dominated universe before we knew about dark energy. And in fact, the universe was matter-dominated from when it was about 72,000 years old to when it was about 9 billion years old. So that's when the matter density was the highest of the three. Go back before 72,000 years, and radiation dominated the universe. Most of the energy density was in the form of radiation before that point. So that's the history of the universe in a nutshell in terms of the energy densities. Yes?
How again does the radiation go over like 1/8?
It goes like 1/8⁴, because the number density of photons goes like 1/8³. Because if you just take a specific example, if you go from now when the scale factor is 1 to sometime in the future when the scale factor is 2, the cosmic ray photon, their number density, there will be 1/8 what it is now, because every 1 cubic meter co-moving volume in between the galaxies now will have expanded to be 2 meters by 2 meters by 2 meters then. So it'll be 8 times as big. So that alone would make the energy density be 1/8, 1/2 cubed, as big as it is now. That's the whole story for matter, because it's just a matter of the particles getting more spread out from one another, but they keep their masses as they spread out. So mc squared for the particles stays the same. On the other hand, remember that the wavelength of a photon is stretched by the expansion of the universe. So each cosmic microwave background photon will only have half as much energy when the scale factor is 2 as it does now. That's another factor of 1/2 in the energy density, so it'll only be 1/16 as big, 1/2 to the 4th times as big as it is now. And so I've said it all, you understand it all, it's great. Let's go ahead and put it into the notes. Make it something we have to refer back to. Math time, or at least write it on the board so you've actually got some notes time.
It's my favorite feature on it.
No, you don't mean, that's right. I'm afraid we're gonna have to use math.
And there was much celebration.
Why?
Because it's the language of the universe. Righty then. So, evolution of the energy density. The matter density varies with the scale factor according to epsilon sub matter as a function of the scale factor is epsilon matter naught. In other words, the matter density now, remember the naught subscript means now when the scale factor is 1 by definition, over a cubed. Since a co-moving volume is a cubed times larger in volume than it is today. Of course, if you go backwards, a cubed times larger really means smaller, right? In other words, if a was 1/2, it would be 1/8 times larger. In other words, it's really smaller than it is today. So that's a little bit sloppy to say larger in volume than it is today, but I hope you know what I mean. So when you divide the energy, when you find the energy per unit volume, it's only 1 over a cubed what it is today. Okay, is that clear? You okay with that? Okay. Okay. The radiation density obeys epsilon r as a function of the scale factor is epsilon r naught, its value today. We're working to the 4th power. Since the number density of photons here. It's almost all in the cosmic microwave background. Goes like 1 over a cubed, and energy per photon, hc over lambda, goes like 1 over a, since lambda is proportional to the scale factor. As the universe expands, the wavelengths increase, and so their energies go like 1 over a. So overall, you got 1 over a times 1 over a cubed for the energy density and radiation. So not only do the photons spread out, their energies decrease as well, so the radiation density falls faster than the matter density. And the energy density of cosmological constant would be, well, constant. Would be, well, constant. Since it's an energy associated with empty space, and a cubic meter is a cubic meter. As space expands, more dark energy is created. So in general, we'll write the total energy density as the sum of all the various components. And are you puzzled by something there?
Yeah, I just don't understand why you wrote cubic meters and cubic meter.
What I mean by that is when you say like in this, yeah, obviously that's a, but in other words, a cubic meter is a cubic meter is a cubic meter. As we make more cubic meters, each one has the same amount of dark energy in it. So as the universe expands, the total amount of dark energy is increasing, and so the density stays the same. That's what I'm trying to say.
Okay.
By that, yeah, so that kind of code or something like that. In general, the total energy density is epsilon will be the sum over W of epsilon W. So in other words, we imagine we've got various energy densities described by various equation of state parameters. So W is the equation of state parameter. We use to label an associated energy density, an associated, say, type of energy density. over all the equation of state parameter values that exist in our universe of each partial pressure, if you will, the pressure due to each component, and that'll be matter, dark, and that's going to be matter, energy, and I'm sorry, matter, radiation, and dark matter, effectively, the three pieces. And since our equation of state is P is W times epsilon, we can write it as the sum of the W times epsilon W. Because our nice simple equation of state parameter is that the pressure is just some multiple W of the energy density, where W takes on the values we gave before for non-relativistic gas and radiation and dark energy. Logical constant. What questions do you have? So let's review. What is W for non-relativistic gas in our approximation? Like the air in this room. How does the pressure compare to the energy density? So, what's the pressure of the air in this room? Give me a number. So I'm going to call it 10 to the 5th pascals, right? So that's, put that in terms of joules per cubic meter. What's a pascal? What's the units of a pascal? Newtons per square meter, right? And you can also call that joules per cubic meter, dimensionally speaking. So the pressure in terms of joules per cubic meter, which puts it in the same units as energy density for the air in this room, is about 10 to the 5th. The density of air is something like a kilogram per cubic meter, so what's its energy density? What's the energy density of a, if I have a kilogram per cubic meter of mass, what's the associated energy density? What do I multiply by? What? No. I want to convert mass density into energy density. What do I do?
MC squared.
MC squared. So if I've got a kilogram of air in a cubic meter, what's the equivalent energy density? 1 kilogram times what number squared? Speed of light. What's the speed of light? What's that squared? 9 times 10 to the 16th. So the air in this room has an energy density of about 9 times 10 to the 16th joules per cubic meter and a pressure of about 10 to the 5th joules per cubic meter. How does the pressure compare to the energy density? Very much smaller. So what did we say W was relating pressure and energy density for non-relativistic gas? It's basically what?
Zero.
It's basically 0. So what did we say W was for non-relativistic gases? Because the pressure is negligible compared to the energy density, we just said, let's just call W. No. If I'm going to say P is epsilon, is W times epsilon, and I'm saying the air in this room, for purposes, for gravitational purposes, for the contribution to the, for the pressure's contribution to gravity, remember this term, it's epsilon plus 3p, okay? We said P is negligible compared to epsilon. So if we're going to say P is W times epsilon, and P is negligible, so tiny it's practically 0, what am I making W? 0! Yes, W is 0 for non-relativistic gas. W is 0 for non-relativistic. Not exactly, but we're just going to call it that. It's an awfully good approximation. What about for radiation? The pressure of radiation, from the pressure integral, we just quoted it last time. Pressure is 1/3 the energy density. So what's W for radiation? 1/3. 1/3. And what was it for dark energy if it's a cosmological constant? 1. No. What did we say about the pressure associated with cosmological constant? What's very fundamental about that pressure? It's a pressure.
Negative pressure.
Negative pressure. It's a negative pressure. And P was equal to
Negative percent.
epsilon, so what's W for cosmological constant? -1. So typically our sums are going to be over W equals 0 for non-relativistic gas, for matter. W is 0 for matter. W is 1/3 for radiation. W is -1 for dark energy. So this sum is effectively going to be over the values of W equals -1, comma, 0, comma, and 1/3. Those three values of W are what's in the sum, because those are the three energy densities that we're talking about. Okay? All right, so, but just keeping things generic for now, just saying, okay, there's a bunch of W values for different components of the universe. Then let's look at what the fluid equation says. The fluid equation, that was equation 4. So let's remind ourselves, the fluid equation 4 is, dig it up for myself here, epsilon dot plus 3a dot over a times epsilon plus p is equal to 0. That was the fluid equation. Let's plug in our expressions for epsilon p and p over there. We're just going to sum over W. Sum over W of epsilon sub W dot plus 3 a dot over a epsilon W plus PW is equal to PW is equal to 0. So I just substitute our expressions for epsilon and P into the fluid equation. Since that equation is linear in all the derivatives and quantities, it applies to each term individually. By which I mean each W value will satisfy that equation. So for each W value, epsilon W dot plus 3 a dot over a, epsilon W plus PW is equal to 0. And certainly you can see that would work, right? If each term satisfies the equation, then certainly the sum will satisfy the equation. And in fact, the linearity can be used to show that's the only possibility, that each term has to satisfy that. So we're going to multiply through by dt and rearrange to obtain. So if I remember that epsilon W dot means d epsilon W dt. So I'm going to multiply through by dt. So that becomes, after we rearrange it, d epsilon W over epsilon W is equal to -3 times 1 plus W dA divided by A. because of the fact that PW is W times epsilon W. In other words, we've got a separable differential equation because we've got the epsilon W terms on one side and the A terms on the other side. Is everybody happy? So we can integrate this sucker. Integrate both sides. So we'll need to throw in an integration constant, integrating both sides. What's the integral of d epsilon W over epsilon W?
Is that
What's the integral of d epsilon W over epsilon W? In other words, if I do this,
Natural log.
got it, yeah, right? Natural log of epsilon W equals, same deal over here, you're integrating dA over A, so we get minus 3 times 1 plus W, natural log of A, plus C, where C is an integration constant. So now we exponentiate both sides. What's e to the natural logarithm of epsilon W? Yeah, it's just epsilon W, right? Exponentiation and natural logging are inverses of each other. So epsilon W is, it'll be e to the natural logarithm of A to the power of minus 3, well, I'm going to simplify that, 1 plus W times e to the power of the integration constant. Right, so in other words, I'm just doing it you might see what it is just immediately, but just to be explicit, if I exponentiate a sum, that's the product of the exponentials, so I'm taking, and then also e to the xy is e to the x to the y. So I can say it's e to the log A to the power of minus 3, 1 plus w. So in other words, epsilon w is what's e to the log A to the power of minus 3 times 1 plus w times that e to the c there. And since epsilon w naught, its value today, by definition that's epsilon w when a is equal to 1, we have that e to the power c is equal to epsilon w naught. In other words, just plug in a equals 1 in this equation. That says epsilon w equals, epsilon w naught is equal to e to the c, because 1 to the power of minus 3 plus w is 1. epsilon W is epsilon W naught over A to the power of 3 times 1 plus W. That's a box-worthy equation that we shall designate equation 6. So if I know the equation of state parameter, this tells me how that energy density varies with time. So let's try it for some cases we've already talked about. W equals 0, what's that for? Is that matter, radiation, or dark energy? Matter, because relativistic matter we count in with radiation. So that's for matter. This would say that epsilon for matter would be equal to epsilon matter naught over A to the power 3 times 1 plus 0. So it's epsilon matter naught over A cubed. Is that what we got before?
Yes.
It is what we got before. Check. Smiley face.
So,
Star.
looks like we're taking the square root of smiley face stuff.
That's just your imagination. It's
Oh.
imaginary or something like
I
that.
don't know.
Galaxy. Right. Frosted Lucky Charms.
Magic.
W equals 1/3. What's that?
Radiation.
Radiation.
Rad.
That's rad, yes. Epsilon rad equals epsilon rad naught over A to the power of 3 times 1 plus 1/3. That's epsilon rad naught over A to the 4th power. Because 1 plus 1/3 is 4/3 and 3 times 4/3 is 4. Does that work? Yeah, that's what we got before.
Yeah.
Yeah.
Now I have a solution.
Oh, my goodness.
Okay, now that passes what present.
W equals minus 1. What's that? Dark energy, or at least cosmological constant, because the dark energy doesn't have to be a cosmological constant. So it would be specific cosmological constant. Why that says that epsilon, we'll call that lambda, is equal to epsilon lambda, big lambda, right? In other words, cosmological constant lambda, over A to the power of 3 times 1 plus minus 1. In other words, epsilon lambda naught. Right, because it's A to the 3 times 1 plus W. If W is minus 1, that's A times A to the power of 3 times 0. A to the 0 is 1, right? So it says that epsilon lambda is equal to its value today at all times. Do I put a check mark next to that?
Yes.
I surely do. So it's all worked out beautifully. BEA beautiful.
That's,
Am I-
that's how I first learned how to spell it. Way back when.
Oh yeah, really? Oh yeah.
I don't know, there's some mighty thing.
One of my roommates in college, one evening that he just got into that mode, he goes, BEA beautiful. BE beautiful. BEAU tiffle. And he's just like going on and on. Just like, what a weird place. I don't remember if that's before or after the time when he sat up in bed and said, "Good night, sweet princess," and then lay back down and relaxed.
I reiterate. What a weird.
Oh, seriously?
I've got some weird roommate stories. They all come from freshman year. Yeah, exactly. After that, you get to decide who you.
This was senior year, so we chose it.
Oh, maybe you were the sweet princess.
I was not, as a matter of fact. I'm pretty sure I was not.
But did you ask?
No.
There.
Remember you asked our what were we
So the WMAP satellite says current temperature at the cosmic microwave background is 2.725 Kelvin.
You know, it-
No. So that says that the current energy density of the cosmic microwave background radiation, you may recall from last semester, that's the radiation constant times the temperature to the fourth. That's the energy density of black body radiation, and CMB is basically the best approximation of black body radiation we know of. So we can run the numbers and get 4.17 times 10 to the minus 14th power joules per cubic meter. Which is 0.260 MeV per cubic meter. Right, whereas we need about 5,200 MeV per cubic meter for the universe to be flat. So certainly the radiation density is not enough to make the universe flat, but nobody's claiming it is. But we can associate a density parameter with the CMB. So omega density parameter for the CMB today, which remember would be its energy density divided by the current critical energy density. And that gives us about 5.0 times 10 to the minus fifth power. Because remember, this was something like 5,200 MeV per cubic meter.
This might be the question, but where did we encounter AT or 14?
Last semester we were talking about black body radiation. So remember that the flux is sigma t to the fourth, and the energy per cubic meter is AT to the fourth. Where A is the radiation constant, which is like sigma something over something, it involves sigma, but it's some combination of sigma and other stuff. This is muchly bigger than the contribution from starlight.
This is much bigger.
Yes. Yeah, if you prefer, you could say much bigger or whatever, yeah. It's huge.
It's so huge.
I'm using it now.
And the contribution from starlight which turns out to be epsilon sub starlight 0 is about 10 to the minus 15 joules per cubic meter, or about 0.007 MeV per cubic meter. So there's way more radiation, it turns out, in the CMB than there is in starlight. Way more energy in starlight than starlight. Let's go ahead and take our break at this point. And so moved. Second? What? All in favor signify by standing up. There we go. Okay.